One of our last lessons in the note pack talks about Graham's Law of Diffusion. Our note packs are open to page 11, about halfway down. We see diffusion and effusion, a couple of vocabulary words introduced right at the start of our new unit, the gas laws. That term diffusion, that tendency for gases to travel from an area of higher concentration to an area of lower concentration until, of course, an equilibrium is reached. I bet on the very first day of our note pack, we introduced the concept of the kinetic molecular theory. Molecules are in motion. I placed an ammonia and a hydrochloric acid cap near each other, and we saw a white cloud diffusing throughout the room. Diffusion, the tendency of molecules to move from an area of high concentration to an area of low concentration until an equilibrium is reached. If the term diffusion is occurring through a tiny pinhole, diffusion of gases through a pinhole is known as effusion. So that motion of molecules moving from high to low concentration until an equilibrium is reached. Of course, we're writing these definitions into our note pack. Today's lesson on Graham's law allows us to figure out the relationship of velocity related to molar masses of gas. So let's take a look at Graham's Law of Effusion. Moving to our next slide. Graham's Law of Diffusion is stated as the ratio of velocity of a lighter gas to a heavier gas, and it's equal to the square root of their inverse of their molar mass. I know that's a mouthful. I'll read it again as you write. The ratio of velocity. How fast is one gas moving compared to another? If you don't like the word velocity, just think of it as speed. The ratio of speed, the ratio of velocity of a lighter gas based on its molar mass compared to a heavier gas based on its molar mass. We can calculate that ratio of velocity by simply taking the square root of the inverse of their molar masses. I know Graham's law is a mouthful to say, but it's actually quite easy to use. Let's take a look at the mathematical proof of Graham's law. And to do that, what I'd like to do is share with you on the document camera. On the document camera, I'm going to share with you the mathematical proof of Graham's law. So we're right about here, page 11. Here's what we know. That kinetic energy, the energy of molecules in motion, has a formula we introduced right on the first day. We said it's 1/2 the mass times the velocity squared. 1/2 mv squared. Now I know that I'm writing large so you can see it on the screen, so I'm going to simply put another piece of paper on here so I can make a lot of room. Kinetic energy, I can also write that as Ke, is 1/2 mv squared. Now remember, V all throughout our unit has been on volume. The V's in the Puvnerts and in the gas law equations have been volume. But notice here, V stands for velocity, or speed with which the gas moves. When two gases are at the same temperature, they have the same average kinetic energy. At same temperature, let's say we have the kinetic energy of gas A set equal to the kinetic energy of gas B. And just so we are all on the same page, let's call gas A the lighter gas based on its molar mass, and gas B will be the heavier gas based on its molar mass. I'm going to sub in the kinetic energy formula and derive Graham's law with you, so please keep writing down everything I do. If kinetic energy is 1/2 mv squared, the kinetic energy of gas A is exactly equal to the kinetic energy of gas B as long as they're at the same temperature. We want to manipulate this algebra, this equation, to get the ratio of velocities. The ratio means the lighter gas speed set over the heavier gas speed. That's our target. Now notice right away what we can do. According to the laws of algebra, we can simplify those 1/2s, can't we? They simplify right out of the equation because they're the same number on both sides. So gone. Now keep in mind, in the next step, I want to move velocities to one side, so let's divide both sides by VB squared, just simply to eliminate it from one side and bring it over to the other. I want the ratio of velocities. VA squared set over VB squared is a ratio, a comparison of the speed of those two gases. And I also want to bring the m's over to the other side. So again, let's divide both sides by the mass of the gas A. See what's happened? These have now canceled. Let's rewrite, kind of clean it up. What do we have so far? The velocity of gas A squared over the velocity of gas B squared is equal to mB over ma, where m is the molar mass, just the weights off the periodic table. Now notice I want the ratio of velocities, not squared, but by themselves. So now let's take the square root of both sides. And by doing that, we're getting rid of the squared signs for the velocity. Again, let's rewrite, kind of cleaned it up. VA over VB is equal to the square root of MB over MA. That is the derivation of Graham's law of diffusion. Now let's make sense of this, because it is kind of scary at first, but very easy to use. Now keep in mind what we've just said. The ratio of velocity, that means we're taking a fraction, aren't we, of the lighter gas A compared to the heavier gas B. The lighter gas to heavier gas, that ratio of velocity of a lighter gas compared to a heavier gas is equal to the square root, see that? That was necessary because in the kinetic energy formula, velocities were squared, is equal to the square root of the inverse of their molar mass. Notice here, A is on the top, so A is on the bottom. That's what inverse means. B is on the top, B is on the bottom, on the opposite sides of the equal sign. Graham's law of diffusion. How fast does a lighter gas go compared to a heavier gas? How fast is it moving? We can simply calculate that ratio of velocity by taking heavy over light, square root key. Just a little molar mass calculation. What we've just written out, I know that's a lot to fit into this area. I want it all in there. You can even leak down here. And if I simply say Graham's law in a little bit easier words, that relationship of the lighter gas to the heavier gas, Graham's law is telling us lighter gases travel faster than heavier gases. And we can use Graham's law of diffusion to calculate how much faster they're going based on their molar masses. The ratio of velocity of a lighter gas to a heavier gas is equal to the inverse of the square root of their molar mass. That's Graham's law. The ratio of velocities. Lighter gas is A, the heavier gas is B. We solve for VA over VB and we get a number. That number tells us how much faster is one gas traveling compared to the other. Let's put it into action. Let's show you Graham's law isn't so scary at all. In our first example problem, top of page 12, we're asked to place the following gases in order of increasing average molecular speed. They're all at the same temperature. So the 25 Celsius is just letting us know they're all at the same temperature. All we really need to do is go to work and find the molar masses of each of these molecules and the increasing average energy, increasing average molecular speed. Lighter gases travel faster. And so with that note, we're going to go from heaviest to the lightest. Heaviest to lightest would show us the increasing average molecular energy. So here we have Ne, neon, with a formula mass of 20.2. Let's just record that. Neon, 20.2 grams per mole. HBr, what is its molar mass? Well, here's bromine at 80. We can call it 79.9 plus one more for the hydrogen. So again, these are just estimates, so I'll put 81 grams per mole. We have SO2. SO2, again, finding molar mass, we have 32 plus 16 plus 16. That's 64. We have NF. Nitrogen at 14, fluorine at 19, so let's add that one. 14 plus 19 times 3, that's a molar mass of 71. And the last one is carbon monoxide. We have carbon at 12, oxygen is 16, so that's 28 as its molar mass. And now we're ready. We have the weights of each of these molecules, gaseous molecules at 25 Celsius, about room temperature. Who's the lightest of them all? It definitely is going to be traveling the fastest. Who's the heaviest of them all? Looks like HBr. It's definitely going to be traveling the slowest. Heavier gases move slower, lighter gases move faster. We want to go from heaviest to lightest. In other words, that's the same as saying slowest to fastest. And let's rank them. First, we have HBr. It is heavier, so it's traveling slower as, who's next? NF. Oops, I forgot the NF3. There we go, NF3. Who's next? Looks like sulfur dioxide is slower than. Looks like carbon monoxide, and the fastest one of all, neon. We've ranked them from heaviest to lightest, slowest to fastest, just based on the molar mass. As long as gases are at the same temperature, lighter gases travel faster. Graham's law of diffusion, simply formulated from the kinetic energy formula. In our second example, we want to know the rate of diffusion of nitrogen gas compared to helium gas. So nitrogen gas, of course, is diatomic. It has a molar mass of 28. We're going to compare that to helium, who has a molar mass of 4. So just finding molar mass, nitrogen is diatomic, so 28. Here's helium, molar mass of 4. We already know that helium is going to travel faster. The ratio of a lighter gas, which in this case is helium, compared to the heavier gas, which is nitrogen, is equal to the inverse of their molar mass, square rooted. So the heavy over light under the radical. Notice how I have them all labeled. We're solving for this ratio of velocity. This one number is going to tell me how much faster helium travels. Square root of 28 over 4. Square root of 28 over 4 is 2.6. Now look at, I want us to write a sentence so I know you know what that number means. What that means, helium is traveling, write this with me, 2.6 times faster than nitrogen. That's our answer. We solve for the ratio of velocity. Helium zipping along 2.65 times faster. 28 over 4, square rooted. And we find our ratio of velocities. Let's try another. Compare the rate of diffusion of argon to neon. Argon to neon. Argon is a noble gas, Ar. It has a molar mass of 39.9. Neon gas, again, is a noble gas. right above it, and it's 20.2. Who's traveling faster? Well, of course, the lighter gas travels faster. Let's calculate how much faster. The ratio velocity of the lighter gas compared to the heavier gas is equal to the inverse of the square root of their molar mass. Heavy over light, square root key. That's all I'm saying. The heavier gas is 39.9 grams for argon. Over the lighter gas, its formula weight of 20.2 grams of neon. Heavy over light, square root. The square root of the ratio of 39.9 over 20.2. Ratio of the heavy over light, square rooted, is 1.41. Now in a sentence, write out what that number means. We know that neon is traveling 1.41 times faster than the heavier gas of argon. Now in a sentence, I know you know what that number is standing for. Let's read through example 4. Looks like this is a little lengthier. A gas of unknown molecular mass was allowed to effuse through a small opening at constant pressure conditions. It required 105 seconds for a whole liter of the gas to escape through that hole, to effuse. Under identical experimental conditions, it required 31 seconds for oxygen to effuse through the same hole. Calculate the molar mass of the unknown gas. Remember that the formula, the faster the rate of effusion, the shorter the time to escape through that hole. Let's talk about that. Velocity is speed. Velocity is defined as distance traveled over time. Write this down in your notepad. Distance over time is the definition of velocity. They're really telling us about the ratio of velocities by giving us the information about the time it's taking for the molecules to escape. If some unknown gas took 105 seconds, and oxygen did the same thing in only 31 seconds, who's traveling faster? Remember, the distance is the same. Alrighty, if the distance is the same for both, they're in the same race. I'm moving from point A to point B, and oxygen crosses the finish line 31 seconds, and some unknown gas lollygags and takes 105 seconds to cross the same finish line. Clearly, this unknown gas is the heavier molecule. Oxygen must be the lighter molecule. So here's what we know. The ratio velocity of the lighter gas to the heavier gas, which we don't know its identity, so let's just call it heavier gas. We'll just use that generic B, for B is the heavier gas. It's equal to the inverse of the relationship of heavy over light, molar mass. And remember, that's what we're trying to solve for. The molar mass of the heavier gas is the target variable, set over the molar mass of the lighter gas, which we've determined to be oxygen, simply because it travels 31 seconds in the same distance that the other gas took 105 seconds to do the same distance. So of course it's going to be the lighter gas. So let's think about what we know. Oxygen's ratio velocity is given to us really as 31 seconds. Where does that fit? If the distance is the same, let's just put 1. They're traveling 1 meter, if you will. So it now is 1 over 31 seconds. That's its velocity. What about the heavier gas? It traveled the same distance. As long as these numbers are the same, they're just going to fall out of the equation. And it took 105 seconds to do the same race. This is the VO2 over the V for the heavier. The velocity of oxygen, 1 over 31. The velocity of the heavy gas, 1 over 105. We're looking for the heavier gas, and we know this one to be 32 grams per mole. Let's simplify what we know. 1 over 31 over 1 over 105 is equal to x over 32. That's really what we have so far. Alrighty. So simplify the left-hand side. What do we find when we simplify this whole thing? 1 divided by 31 divided by 1 divided by 105, and we get a number. There's that left side simplified. I'll say that that is 3.39 is equal to the square root of x over 32. That's what we've done so far, just simplified that ratio. By the way, those of you who are math savvy know that you can simplify simply by going 105 over 31, and you're going to get the same number. All this does is take the reciprocal. Either way, we get the same answer. How do we get rid of the radical? We're going to square both sides, aren't we? Squaring both sides gets rid of the radical. So now we just square that answer. And what do we find? If I square, I have 11.47 is equal to x over 32. We got rid of the radical by squaring both sides. Now to pull out x, we're going to cross multiply. 11.47 times 32, and we get our molar mass, 367.1 grams, a very heavy molecule. The molar mass of that heavier molecule has been identified. So that was our first time where velocity was given to us a little bit differently. They gave us the ratio of velocities in a little different way by talking about time. The lighter gas crossed the finish line much quicker than the heavier gas. We simplified the left-hand side to find that number. The number of the ratio of velocity says that lighter gas is traveling 3.39 times faster than this unknown heavier gas. With the laws of algebra, we pulled out the formula mass of our unknown, much heavier compared to the oxygen. That number makes sense. How about example 5? Again, a little bit different. An unknown gas composed of a homonuclear diatomic molecule, the same atom hooked to itself. It fuses at a rate of 0.355 times as fast as oxygen. Calculate the molar mass. Well, here's what I'm noticing, that the ratio of velocity is given to me as a number less than 1. So when that happens, the whole Graham's law is kind of flipped. The ratio of velocity of the heavier over light is equal to the molar mass of A over B. So notice it's still the same thing, but this is now 0.355. If the ratio of the velocity is less than 1, the lighter over heavier is under the radical. If the ratio of velocity is greater than 1, then we would go back to what we introduced. So I'm trying to show it both ways to make sure you're seeing how math works. Alrighty, so just kind of good notes. This is saying, okay, you know what? That lighter gas, it's going to be placed on top to make sure that this ratio is coming out in decimal form. So let's kind of talk about what we have. We have a ratio of velocity given to us as 0.355. The oxygen, now it goes on top because it's the lighter gas. Its molar mass is 32. We'd like to solve for the heavier gas and identify it. Well, I know that horses need oats for clear brown eyes. Those are the 7 homonuclear diatomic molecules. This X had better match one of those guys' formula weight. Alrighty. So first thing, let's get rid of the radical. We're going to square both sides. 0.355 squared is equal to 32 over X. The X, of course, comes up here. 0.355 squared X is 32. X is 32 over 0.355 squared. Let's see what we find. 32 divided by 0.355 squared is equal to 253.9. So now who's going to match? Well, obviously hydrogen is 2, 28, 32, 38, 71, 160. How about iodine? 127 is its molar mass. A couple of times over, and there it is. That's 254 grams. That's the identity of our unknown gas. So noticing that 0.355 gave me a ratio of less than 1, Graham's law flipped around. If the velocity is greater than 1, we put lighter over heavier. Good margin notes. I'd be sure to write that down. That ends the Notepack lesson. What I'm going to ask that you do now is find your practice test A, and we're going to work those together. Pause the video if you need to. Practice test A should be close by. We're going to open it up to example from page or objective 4. Pause if you need to. Find objective 4 and practice A. Applying Graham's law to problems of rates of effusion. The first question, very similar to the first one from our Notepack. We'd like to place the following gases in order of increasing average molecular speed. Increasing speed, we want to go from slow to fast. We want to go from heaviest to lightest. Carbon monoxide, sulfur hexafluoride, chlorine gas, diatomic, and hydrogen bromide. I'll put it over here. We need to just find their molar masses so we can rank them from heaviest to lightest. So CO adds a 12 to a 16. Carbon monoxide is 28. Sulfur hexafluoride would be 32 from the sulfur plus 19 times 6. That has a molar mass of 146 grams. Chlorine is diatomic, so 71, and this one we calculated earlier is 81. So I've just recorded the molar masses of each of our gases. Who's the heaviest? Of course, HBr would be traveling slower than. Looks like chlorine would come in second place. Oh my goodness, way over here. Good thing I left room. SF6 is the heaviest, 146. Then HBr, then Cl2, and then in first place is the CO. There's the correct. Heaviest to lightest is slowest to fastest. Number 2. Calculate the ratio of the velocity of helium to chlorine. Helium to chlorine. Helium is a noble gas with a molar mass of 4. Chlorine is a diatomic molecule, molar mass of 71. Since we're finding the ratio velocity, I'll place the lighter gas over the heavier gas to find how much quicker the lighter gas is. And we'll do that by simply taking the inverse of the molar mass. So I'll place chlorine on top and helium on the bottom. And we're finding this ratio. How much quicker? Remember, if we had flipped it around, you're just going to tell me how much slower chlorine is. Putting the lighter gas on top tells me how much quicker it is. So I'll just take square root of 71 over 4. And that ratio is 4.2. But write a sentence so I know you know what that means. Helium is traveling 4.2 times faster than chlorine. Lighter gases travel faster. Graham's law of diffusion. Number 3. A certain gas effuses 4 times as fast as oxygen. What is the molar mass of the gas? Notice 4 is the ratio of velocity and 4 is greater than 1. So since the ratio is greater than 1, the lighter gas must be on top. So our formula, heavy over light square root. Unlike the notepad example that gave us a ratio less than 1. Here's a number greater than 1. Here's our formula, lighter over heavier on the ratio side. So a gas is moving 4 times faster than oxygen. Oxygen must be the heavier gas. The oxygen is moving slower. The molar mass of the lighter gas must be on the bottom. Just looking at the inverse relationship. A gas is moving 4 times faster than oxygen, heavy over light, square root key. So what does this algebra look like? We're going to square both sides, aren't we, to get rid of the radical. So 4 squared x equals 32. The x comes up here. X is 32 over 4 squared. Let's hit 4x. 32 over 4 squared is 2. 2 grams is the molar mass of our lighter gas. Lighter gas molar mass is all I wrote for study notes. Number 4. During an effusion experiment, it took 75 seconds for a certain number of moles of an unknown gas to pass through a tiny hole. Under the same conditions, the number of moles of oxygen took 30 seconds. What's the molar mass of the unknown gas? Clearly, oxygen must be the lighter gas. Again, going from point A to point B, it's a race. Oxygen did it in 30 seconds. The other gas did it in 75. So this unknown traveled the same distance from point A to point B, but now it took so much longer, it must be the heavier gas. So the ratio velocity of the lighter gas to the heavier gas, I'll call heavier gas B, it's an unknown, is equal to the molar mass of the heavier over lighter. Let's plug in what we know. The velocity of oxygen is going to be denoted as 1 over its time of 30 seconds. There's the velocity, distance over time. Set over. The time here for the heavier gas was 75 seconds. The ratio velocity, the velocity of oxygen set over the velocity of the heavier unknown. Of course, this is the x that we're targeting, and the molar mass of oxygen is 32 grams. Let's simplify what we have on the left-hand side. And again, we could hit 1 divided by 30 divided by 1 over 75, and we get a number, 2.5. Perhaps those who can simplify algebra quickly, you could do the same by simply taking 75 over 30 and you get the same answer. So whatever works best in your head, simplify the left side and we get 2.5. That's the ratio of velocity. Is equal to the heavy over light, which we know to be oxygen. Its molar mass is 32. Let's square both sides to get rid of the radical. 2.5 squared is x over 32. 2.5 squared times 32 is our x. Just showing the algebra steps that we'll hit on the calculator. 2.5 squared times 32 gives us a molar mass of 200 grams. The molar mass of the heavy gas. Fix that quick. 200 grams is the molar mass of the heavy gas. Maybe you're laughing. One more, number 5. A certain gas A traveled in a diffusion tube. Let's kind of model what I've got. Draw this with me. I've got a diffusion tube with this just a piece of glass tubing. And I'm going to introduce gas A at exactly the same time as gas B. Very similar to the demonstration this started with. Gas A traveled 15 centimeters. In the same amount of time that gas B took 10 centimeters to travel. Calculate their experimental ratio of velocity. Gas A traveled 15 centimeters before it hit gas B, and when they hit, you'll see this cloud form, that white diffusion cloud demonstrated from the start of our chapter. If velocity is defined as distance over time, time is held constant. We said on your mark, get set, go! And we introduced A and B into this diffusion tube at exactly the same time. So time is the constant. Let's just call it 1. I mean, any number works because it's the same time. Here's what we now know. Which one must be lighter? Which one must be heavier? Well, golly, look. A made it 15 centimeters in the same amount of time that B only made it 10. A must be the lighter gas. B took its sweet old time, heavier gas. In the same amount of time, it only made it 10 centimeters. So, of course, A must be lighter. It went farther in the same amount of time. So, in other words, this distance for the lighter gas over heavier gas, 15 centimeters is the distance. Let's just call time 1 second. It doesn't matter. It's going to fall out of the equation. Here's the gas A velocity. Here's the gas B. 10 centimeters set over the same time. Make sure those numbers are the same. It's going to fall out. And there's the ratio of gas B. What did we just do? We'll see how these just simplify. They're gone. 15 over 10 is a ratio of velocity. Isn't that 1.5? All that's saying, and this is what I want you to write out, gas A is traveling 1.5 times faster than gas B. There is the answer to number 5. So in other words, we're measuring velocity either in distance, or we can measure velocity in terms of time taken to travel. Either one can be pulled out and solved for the ratio. You now have an A+ on your Objective 4 on Graham's Law. I'd like you to work on the next set of problems from Practice Test C.